This video series goes through the daily problems in this maths calendar that is published by the American Mathematical Society. You can either purchase it through their website or via Amazon. Today's problem is as follows. We have an outer circle in blue centered on this point here. We then have 4 inner circles as shown. We are told that the area in here is 23 and we are asked to find the area in here. To solve this problem, we make use of an inclusion-exclusion formula for the area of the union of 2 overlapping sets. Consider 2 sets, A and B, where both these are solid shapes, so they're both filled in. The area of A and B is equal to the area of A plus the area of B minus the area of A intersection with B, this region in here. This should be intuitively clear because the area of A plus the area of B counts their intersection twice. The area of A includes this region here and the area of B includes this region here. So it's been counted twice. So I subtract off 1 copy of the area of A intersection B. If you so wish, you can assume that these regions are rectangular and assign lengths to them and do the calculation yourself to show that this is true, at least for rectangles. A proof will follow near the end of this video. If we apply this formula to 2 intersecting circles with the same radius, we get the total area is equal to pi r squared plus pi r squared minus x. The idea behind the previous formula is that when you add up the area of individual sets, then we count their overlap twice. It should be clear that if we add up the area of this circle, plus this circle, plus this circle, plus this circle, then we've counted each of these overlapping regions twice. Therefore, the area of the union of the 4 circles, the area inside this outside green line here, is going to be equal to 4 pi r squared minus 4x. Indeed, each circle has got area pi r squared, and there are 4 of them, and if we add them all up, then we're counting each of these overlapping regions twice. And by symmetry, the area of each overlapping region is the same. So we have to subtract off the overlapping area just once, so 4 times x. The area of the outer circle, we see that if the radius of these inner circles are r, then the radius of the outer circle is 2r. A line from the center here through here, continued on to here, will have length 2r. So the total area is pi times the radius, which is 2r all squared, which gives us 4 pi r squared. The difference between these two numbers, 4 pi r squared minus, in brackets, 4 pi r squared minus 4x, is going to be the area here plus here plus here plus here. And again, by symmetry, the area out here is the same as here and the same as here and the same as here. So therefore, we see that 4 pi r squared, the area inside the blue circle, minus the area inside the green part is equal to 4 times 23. And the 4 pi r squareds cancel, and we're left with 4x equals 4 times 23, so x is 23, or in words, the area here is exactly the same as the area here. For the rest of this video, first we will prove the inclusion-exclusion formula for 2 sets, and then we will extend it to 4 sets, so we could have applied that formula directly to this problem. One way to prove this formula is to start off by saying the area of A and B is equal to the area of A plus the area of B that does not intersect A. So the C here denotes complement. This is a basic axiom of area. the area of A union B is equal to the area of A plus the area of B whenever A and B do not intersect. That's a basic axiom. By the same axiom, we know that the area of B that intersects with A plus the area of B that does not intersect with A is just the area of B. Once again, we've got two non-overlapping regions, so the area of one plus the area of the other is just the area of the union of this with this, but the union of B intersect A with B intersect A complement is just B. And finally, we just substitute this expression here, which we rewrite in terms of the area of B intersected with the complement of A is equal to the area of B minus the area of B intersect A. We just substitute that into here to get that the area of A and B is equal to the area of A plus the area of B minus the area of B intersected with A, which is just this formula here. This formula can be extended to more than two sets, and the proof requires an inductive step. We prefer using an algebraic method, given next. Method 2 makes use of the characteristic function of a set, which by definition, if we evaluate this function at a point x, we are going to get 1 if that point x is in the set A, otherwise we get 0. So for example, on the real line, for the set A being the closed interval between -1 and 1, the characteristic function will look like this, the red line here, 0 outside of A and 1 on A. The link between this and area is that if we integrate the area under the characteristic function, we get the area of A, which can be seen visually here. And in general, we have this formula here. Don't worry too much about this notation here. You can replace this with just the usual dx in this example here. Roughly speaking, this denotes infinitesimal area. So the area of a set A is given by adding up all the infinitesimal areas making up the set A. And the characteristic function tells us which parts of the set to add up. We add up those that are inside the set and we ignore those outside the set. If we want to use characteristic functions, then we have to reinterpret the union and the intersection of two sets in terms of some algebraic formula for their characteristic functions. The second one is straightforward. We claim it equals the product of the two individual characteristic functions. To see this, let's evaluate both sides and compare. If we pick any x, there are only 4 cases. Either x does not lie in A and does not lie in B, or it lies in A and not B, or it lies in B but not A, or it lies in both A and B. For each of these 4 cases, we can evaluate the characteristic function of A intersect B, which will be 0 except when x is in both A and B. And then we can do the same for the characteristic function of A times the characteristic function of B. If x is not in A and not in B, then the characteristic function evaluated at x for A will be 0, and this one will be 0. If it's in A but not B, we have 1 times 0, 1 because it's in A, 0 because it's not in B. If x is not in A but in B, then we've got 0 times 1 because it's not in A but it is in B. And if x is in both A and B, we have 1 times 1. And so we see that this is equal to this, 0, 0, 0, 0, 0, 0, 1, 1. To find this one directly is a little bit tricky, but we know that the complement of A union B is equal to the intersection of A complement and a B complement. This can be seen by drawing a picture. If something lies outside both A and B, then it must be outside of A and it must also be outside of B. And conversely, if something lies outside of A and also lies outside of B, then it must be outside both A and B. The reason we thought to write this down is because we know how to handle characteristic functions of the intersection of two sets. We don't know how to handle complement, but a moment's thought shows that the characteristic function of A complement is just 1 minus the characteristic function of A, because 1 minus 1 is 0 and 1 minus 0 is 1. Therefore, by using this formula and this formula and this formula, we can derive an expression for this. Specifically, the characteristic function of A and B is equal to 1 minus the characteristic function of the complement of A union B. And the characteristic function of the complement of A union B is equal to the characteristic function of A complement multiplied by the characteristic function of B complement. And the characteristic function of A complement is 1 minus the characteristic function of A, which is this term here, and the characteristic function of B complement is 1 minus the characteristic function of B, which is this function here, and that gives us the characteristic function of the complement of A and B, and we want the complement of that, so we have one more 1 minus out the front. From the top line, we get the characteristic function of A and B is equal to 1 minus the characteristic function of A times 1 minus the characteristic function of B, which when we expand gives us 1 minus 1 times 1 is 1, 1 times negative characteristic function of B is negative characteristic function of B, minus the characteristic function of A, plus the characteristic function of A times the characteristic function of B, which is equal to the characteristic function of A plus the characteristic function of B minus the characteristic function of A times B, which we know is the characteristic function of A intersect B. If we look closely, we see this is essentially the formula we want to prove. We have characteristic functions here, but instead we want area. If we just replace the characteristic function by area, this would read the area of A and B is equal to the area of A plus the area of B minus the area of A and B. And indeed, all we need to do is integrate both sides of this equation, because integration converts characteristic functions into areas. And integration is linear, so when we integrate these three terms, we get the integral of this term plus the integral of this term minus the integral of this term. That is the second method for proving the inclusion-exclusion formula. The inclusion-exclusion formula applies to more than two sets, and in our problem of the day, technically we had 4 circles that were intersecting. We could call the 4 circles A, B, C, and D, and we wanted to be able to write the area of those 4 circles in terms of the areas of each of the individual circles and the areas of their overlaps. Just like before, we can show that the characteristic function of A and B and C and D is 1 minus the characteristic function of A times 1 minus the characteristic function of B, etc. And if we expand this out just like before, then 1 times 1 times 1 times 1 cancels with the leading 1. Characteristic function of A times 1 times 1 times 1 gives us the characteristic function of A. The sign gets flipped by the negative sign out the front. Same for the characteristic function of B. We've got 1 times the characteristic function of B times 1 times 1. Same for C. 1 times the characteristic function of C times 1. And same for D. 1 times 1 times 1 times the characteristic function of D, giving us the first line. Then pairwise, characteristic function of A times characteristic function of B times 1 times 1. Characteristic function of A times characteristic function of C times 1 times 1, and so forth. So we get every pairing of A, B, C, and D for the second line. And because we have 2 of these terms, negative times negative gives us a positive, and then reversed by the negative out the front. Then we take them in groups of 3, characteristic function of A times B times C times 1, and so forth, and we get the third line. And finally, we have the characteristic function of A times B times C times D, giving us the last line. And whether we have positive or negative depends on how many characteristic functions we have in the expansion. Each one has got a -1 out the front, so the sign keeps changing. Positive, negative, positive, negative. By now integrating both sides, we essentially just replace the characteristic function by area. And we also know that the product of 2 or more characteristic functions is just the characteristic function of the intersection of the respective sets. So we get that this area is equal to the sum of the individual areas minus the sums of the areas of pairwise intersecting sets plus the sum of the areas of any 3 of the sets intersecting minus the area of the intersection of all 4 sets. For today's problem, we had 4 circles and they only had pairwise intersections. So for the individual areas, we get pi r squared for each one. For their pairwise intersections, we had x for some of them and 0 for others of them. Here I'm assuming the circles are labelled clockwise, A, B, C, D. So A and B intersect. A and C do not, they're diagonally opposite. A and D intersect. B and C intersect. B and D are diagonal and do not intersect, and C and D intersect. So at this stage we have got 4 times pi r squared minus 4 times x. Our 4 circles, we don't have any 3 of them intersecting, so these terms are all 0, and also all 4 circles, they don't intersect either. Or technically you can say they intersect in a single point, but a single point has got 0 area. In summary, we could have either said that the area enclosed by the 4 green circles is equal to 4 times the area of each individual circle minus 4 times x, because when we counted the individual areas, we saw that we counted the intersection twice, and the total intersection is 4 times x. Alternatively, we could have used this inclusion-exclusion formula applied to each of the 4 individual circles. Either way, we get the same answer.